Welcome back to the deep dive. Today we're tackling one of the biggest, most expensive problems in training specialized AI. I'm talking about supervision. Finding those high-quality labeled answers you need to feed a model, especially for really complex tasks.
It's a huge wall. People call it the data acquisition wall. And it's where the costs for building a specialized model they just explode.
Right. Like if you want a model that's amazing at legal summaries or clinical guidance.
Exactly. You need human experts to label that data, and that's just not scalable. It's slow, it's expensive, and honestly, it can be really subjective.
Absolutely. So what if you could just skip the human trainer? What if the model could generate its own expert-level training data?
And that's what we're here to talk about. A new method that basically flips that whole equation on its head. It shows that you can directly trade compute power for high-quality supervision.
This is the idea behind a method called compute as teacher, or CAT for short.
And it's a fascinating way for an LLM to create its own training signals. It does it by first doing a kind of deep internal exploration, and then, this is the critical part, reconciling all those different paths to become its own teacher.
So our mission for this deep dive is to really unpack how CAT works. We're going to look at it in two very different, very difficult areas.
First, verifiable tasks. So think high-level math problems.
And then the really fuzzy stuff, non-verifiable tasks, like giving complex medical advice. We want to see what happens when a model turns raw processing power, or FLOPs, into genuinely better data.
To really get why CAT is such a big deal, we first have to break down where the whole supervision process kind of falls apart in the first place.
Okay, so let's unpack that difference between, the black and white problems and the gray ones.
Exactly. So on one side, you have what we call verifiable domains.
Like math?
Math, competitive coding, formal logic, things where you can write a program to check the answer. The reward is simple. It's binary. It's a 1 if you're right, a 0 if you're wrong. The answer is objective.
That's the dream scenario for training, right? The code either runs or it doesn't.
But that's not how most of the world works. The vast majority of useful tasks are in these non-verifiable domains.
And that's where it gets messy.
So messy. We're talking clinical diagnoses, empathetic dialogue, creative writing, policy analysis. There is no single ground truth answer. You could ask 10 experts and get 10 slightly different, but all equally valid responses.
And the current ways we handle that just feel brittle. You either pay a fortune for human annotators, which is slow,
or you try to automate it with another LLM as a judge.
which introduces all sorts of weird biases.
That's the instability.
Yeah.
When you use an LLM as a judge and just ask for a course score, like, rate this from 1 to 5, you get so much noise. These systems suffer from things like verbosity bias.
Ah, right. The judge just likes the longer answer better, even if it's not actually smarter.
It often does. So the model learns to game the system. It gets good at what we call reward hacking, making its answers sound long and impressive instead of just being correct and efficient.
So Kat comes in and asks a really simple question.
A very elegant question.
Yeah.
It says, look, we have a ton of cheap compute, but we have a scarcity of good human data.
Yeah.
Can we just turn that compute into reliable supervision?
And the answer seems to be yes. By running this kind of massive internal peer review, it can generate a teacher signal that's better than what you could get from the outside.
Okay, so this is where we really get into the mechanics of it. The CAT pipeline is basically a two-stage process. I like to think of it as a writer and an editor who just happen to be the same AI.
I love that analogy. So you've got the drafting phase and then this really tough editing phase. Let's start with the drafting, the exploration.
Right, so the model we're trying to improve, let's call it the current policy, right, CAT, it's tasked with generating a whole group of answers to the same question. These are called rollouts.
So not just one attempt.
No, in the paper, they typically used 8. So it generates 8 parallel rollouts. And this is so important because it introduces diversity. You get different ways of thinking, different solution paths, and also a bunch of different mistakes.
Okay, so you have your 8 drafts. Now for the really new part, the synthesis step. This is the editor, and it relies on a second key component, the frozen anchor.
The anchor is the secret sauce. The frozen anchor is the initial version of the model, $P$, and its job is to look only at the group of 8 rollouts that the student just generated.
Not the original question?
No, not the original question. It just sees the 8 answers. And based on those, it synthesizes a single new improved answer. Let's call it 6. And that synthesized answer, 6LR, becomes the new ground truth for training.
Hold on, let's slow down there because that separation feels really, really important. Why does the anchor have to be frozen, and why is it question blind?
That constraint is what creates stability and forces a real critique. The current policy is the student. It's supposed to explore, to learn, to make mistakes. But if the teacher, the anchor, was also changing all the time,
It would be chaos. It would just be chasing the student.
total chaos. So by keeping the anchor, almost frozen, it acts as a stable, unbiased judge of quality. It's a fixed standard.
And being question blind.
That's maybe even more critical. If you gave the anchor the original prompt, what would it do? It would just generate another answer, a ninth draft.
And it might make the same common mistakes as the other 8.
Precisely. By forcing it to only look at the 8 answers, you're not asking it to solve the problem again. You're asking it to be a metacritic, to reconcile the evidence it sees. It has to figure out what parts of each answer are good, combine them, and throw out the errors that only show up in 1 or 2 drafts.
I see. So it's not just selecting the best of the 8 drafts.
No. This is the key. It is synthesis, not selection. Things like best of N or a majority vote, just pick an existing option. CAT constructs a brand new answer. It actively rewrites and corrects.
That's a huge difference, because that means the near answer, $, can be better than any of the individual drafts.
And we saw that in the data. On the math problems, the synthesized answer disagreed with the majority, so different from at least 5 of the 8 rollouts, a full 14% of the time.
Wow. And this is the most amazing part to me. Sometimes it was right even when all 8 of the drafts were wrong.
That happened in about 1% of the questions. That ability to self-correct and find a truth that wasn't even present in any of the individual attempts, that's something a simple selection method could never, ever do.
Okay, so we've used all this compute to create dollars, this really high-quality synthesized answer. How does that then become a reward signal that you can actually use for training?
CAT uses 2 different ways to create a reward, depending on the task. For the verifiable tasks, like math, it's pretty straightforward.
It's just right or wrong.
Right. The synthesized answer, $, becomes the pseudo-answer key. So the reward is simple. A program checks if the new rollout final answer matches the answer in Zillers.
Makes sense. But the real innovation here is how it handles the subjective stuff, the non-verifiable domains. That's what lets it go beyond just math problems.
Absolutely. For those tasks, like the health bench dataset, which is all about clinical chats, they use the system called self-proposed rubrics.
Self-proposed rubrics. So the model creates the answer, and then it also creates the grading criteria for itself.
Exactly. The anchor, $T salt, takes that synthesized answer, $C, and then it generates a specific rubric, $3, just for that response.
And what do these rubrics look like?
They're not vague scores. They're a list of concrete binary yes or no questions. Things like, does the response address all of the patient's initial concerns? Yes, no. Or does it use the correct dosage units? Yes, no.
And by breaking it down like that, you're getting around that whole judge instability problem we talked about earlier.
Yes, you are. Because now you're not asking an external LLM judge to give a fuzzy subjective score like 4 out of 5. You're asking it, in this study, they used GPT-4o to do a much simpler task.
Just check the boxes.
Just check the boxes. Did it meet criterion A? Yes or no? Did it meet criterion B? It's way less prone to bias because you're not judging style, you're judging compliance with specific facts.
So this gives the model much more fine-grained feedback.
It's called shaped feedback. The final reward for the policy is just the percentage of criteria it satisfied. So it's rewarded for hitting specific quality markers, not for just sounding smart.
And the proof is in the results here. The research showed that these rubrics, the ones the AI generated entirely on its own, were just as good as, and sometimes even better than, the rubrics created by human physicians for the health bench dataset.
Think about that. The model is generating its own supervision that rivals or even exceeds the quality of an expensive human expert.
It means the real bottleneck wasn't the model's ability to learn, it was the cost and the messiness of getting that high-quality feedback from the outside world. CAT just builds it internally.
So CAT is obviously a huge win at test time just to get a better answer. But the real power comes when you use it for training. They call this CAT-TRL reinforcement learning with CAT rewards.
And the results, I mean, the numbers are pretty staggering. They tested this across a bunch of different models, Gemma, Quinn, Llama 3.1.
And the gains were not small. For the Llama 3.1 8B model, they saw up to a 33% relative improvement on the Math 500 benchmark.
33% on hard math problems. And what about the medical one, Health Bench?
Up to a 30% relative improvement on Health Bench with that same model. These are massive, massive gains that come purely from self-supervision.
And this next point seems really important. Using this reinforcement learning process, CAN-TRL, was consistently better than just taking those synthesized answers and using them for normal supervised fine-tuning or SFT.
Right, you can't just take that perfect answer, $C, and treat it like a normal piece of training data. SFT is basically just trying to mimic that answer. But the RL approach, with that shaped feedback from the rubrics, is fundamentally more powerful. It teaches the model the principles of a good answer, not just the answer itself.
And that creates what they call the virtuous cycle,
It's a really powerful loop. A better policy generates better, more diverse rollouts,
which lets the anchor create an even better synthesized reference.
which then improve the policy even more. It feeds on itself.
But that leads to a fascinating limitation. If the whole system works by resolving disagreements between the different rollouts, what happens when the model gets so good that all 8 rollouts are basically identical?
That's the ceiling. The teacher signal vanishes. As the policy gets stronger, the diversity of the rollouts naturally goes down. And since Kattni's power comes from resolving that creative conflict, when everyone starts to agree, the learning signal gets weaker and the improvement plateaus.
It's like a group of geniuses who get so aligned they stop challenging each other. But before you hit that plateau, the gains are incredible. Let's make this concrete with that one anecdote from the appendix, the complex number problem.
Oh, this is the perfect example. It's a problem from the Math 500 dataset asking for a value of $0 And in their test, every single one of the 8 rollouts got it wrong.
All of them.
All of them. They all failed because of some small internal calculation error. One divided by 137 incorrectly, another multiplied wrong in a middle step. Little slips.
So any system based on selection would have just picked the best of the 8 wrong answers.
It would have failed, guaranteed. But the synthesized response, it looked at all 8 failed attempts. It correctly identified the systematic calculation errors, but it also saw the correct underlying logic that was present across all of them.
And it fixed the math.
It fixed the math and got the right final answer. It proved it could create a truth that was literally outside the distribution of its own attempts.
That's the ultimate validation of the idea. It's not just filtering, it's genuine knowledge creation. And
Oh.
finally, they showed it all scales. The more compute you throw at it, the more rollouts you generate, the better your teacher signal gets. It's a clean trade-off. FLOPs for supervision.
So to sum it all up, CAT-TI is this really elegant drop-in procedure. It just gets rid of the need for expensive human labels. And it works for clear-cut problems and for those really subjective domains, thanks to the self-proposed rubrics.
It just completely changes the economics of training these specialized models. The bottleneck is no longer data acquisition, it's just affordable compute. CAT-TRL creates this path for models to just continuously improve themselves without us.
And that really leads to a pretty profound thought about the future. I mean, if we can go beyond needing human-written examples, if we can use compute to generate a supervision signal that's better than what we can provide, it raises a huge question.
Which is?
Is this a potential path toward superhuman capabilities? A way for AI to exceed the limits of the knowledge contained in human-generated data?
That is definitely something to chew on. An AI that's not just learning from us, but is actively self-correcting its own collective mistakes to define a new, higher standard of correctness.
That's the potential here. It's unlocking reference-free learning, and it's changing the game for specialized AI.
We encourage you to think about the implications of an AI that truly teaches itself, and we'll see you next time on The Deep Dive.